Okay, so what do you think a skyscraper, a guitar, and even your microwave have in common? It sounds like a riddle, right? Well, they all move to this hidden rhythm, a pattern that's basically woven into the fabric of our world. And today, we're going to decode the fascinating science behind it all, oscillations. All right, let's really get into it. You've got a swaying bridge, a vibrating guitar string, and yeah, the thing that heats up your lunch. What could possibly connect all of these? The answer? Well, it's a fundamental principle in physics. It's a pattern that is, and I mean this, absolutely everywhere once you know what you're looking for. And the answer is oscillatory motion. It's just a constant, repeating, back and forth movement. And believe me, it is everywhere. I mean, think about it. It's in the tiny little atoms vibrating to make up the screen you're looking at right now. It's in the ebb and flow of the ocean's tides, the pistons firing away in a car engine, and yep, even in those huge swaying bridges. It's honestly one of the most fundamental types of motion in the entire universe.
Okay, so to really get a grip on this hidden rhythm, we've got to learn its language, right? So let's start with something super simple, something we can all picture, a perfect swing. We're going to use that to break down the absolute fundamentals of oscillation.
So, picture this, a ball just rolling back and forth inside a bowl. See how it always moves around that central resting point right there at the very bottom? That's it. That's the heart of oscillation. Just a repetitive movement around a central point we call equilibrium. So, how do we actually describe this motion with, some precision? Well, first things first, we need a word for where the ball is at any given moment, and that word is displacement. It's really just the ball's current distance from its resting spot. If it moves to the right, we call it positive. Moves to the left, it's negative. See? Simple as that. All right, next up, amplitude. So imagine you pull that ball all the way up to the very edge of the bowl and let it go. That starting point, that's its maximum displacement. It's the absolute farthest it can get from the center. And that distance, that is the amplitude. It's the peak of the swing. But what about time? How long does one full trip take? From one side all the way over to the other and then all the way back again. Well, that measurement of time is what we call the period. It's literally just the time it takes for one complete cycle.
And to round out our basics, we've got frequency. So this is kind of the opposite of period. Instead of asking how long one swing takes, we're asking how many full swings can we pack into a single second. That's frequency. We measure it in hertz, and it basically just tells you how fast and furious the oscillation is.
Okay, now let's just stick with this perfect little picture for a second. Imagine a world with zero friction, no air resistance at all, a world where our ball in the bowl just swings back and forth forever and ever, never slowing down. Sounds nice, right? Well, physicists have a name for this perfect, idealized kind of oscillation. They call it simple harmonic motion, or just SHM for short. Now, here's what's super cool about SHM. It's all about the energy. Think about it. At the very top of the swing, the ball stops for just a split second, right? At that moment, all its energy is stored up. That's potential energy. Then, as it zips down through the center, all that stored energy turns into motion energy, or kinetic energy. It's this beautiful back and forth trade happening over and over. But the amazing part is, the total amount of energy in the system, it never changes. It stays exactly the same.
Of course, we all know we don't live in that perfect frictionless world. In the real world, swings, well, they stop. So what happens when these perfect oscillations start to fade away? Let's get real. In this next part, we're going to dive into what happens with damping and forced oscillations.
You know how it is. A pendulum eventually stops swinging. A guitar string fades into silence. That's because in the real world, energy is always being lost to stuff like friction and air resistance. And this slow, gradual loss of energy, the thing that makes the swing get smaller and smaller over time, that's what we call damping.
And you can see that difference perfectly right here. On the left, you've got that ideal undamped oscillation, that perfect simple harmonic motion we talked about, where the height of the swing is always the same. But on the right, that's reality. That's a damped oscillation. See how with each swing, the amplitude gets a little smaller and a little smaller until, poof, the motion just stops completely. So how do you fight against this damping effect? Simple. You've got to put energy back into the system. It's just like pushing someone on a swing, right? You can't just give them one big shove and walk away. To keep them going, you have to give a little push at just the right moment over and over again. And that action, applying that regular repeating push, that's what we call a periodic driver force. And it creates something called a forced oscillation.
And this whole idea of pushing at just the right time, well, that leads us to one of the most powerful and frankly mind-blowing phenomena in all of physics, resonance. This is something that can be amazingly useful, but it can also be incredibly destructive. Let's dig into how perfect timing can change absolutely everything.
So, what in the world is resonance? Well, here's the key. Pretty much every object has a natural frequency, a specific rhythm that it just loves to oscillate on. Resonance is the magic that happens when you start pushing that object at its exact natural frequency. You're perfectly in sync with its own internal rhythm. And this classic experiment, called Barton's pendula, shows it perfectly. You've got this big, heavy pendulum swinging back and forth. That's our driver. It's trying to get all those smaller pendulums to swing with it. But just look, most of them are barely moving. But there's one, the one that has the exact same length, which means it has the same natural frequency as the driver. That one starts going crazy. Its swing gets huge, its amplitude just explodes. That is resonance in action. And this graph right here, it shows you the math behind the magic. As the frequency of your push, what we call the driving frequency, gets closer and closer to that special natural frequency of the object, look what happens to the amplitude. It doesn't just get bigger, it absolutely skyrockets, creating that incredibly sharp peak you see. We're talking a tiny bit of energy applied at just the right time, creating a massive, almost unbelievable result.
And this power is something we use all over the place. When you tune a radio, what you're really doing is adjusting a circuit inside to resonate with a specific radio station's frequency. Your microwave? It's blasting food with a very specific frequency that makes water molecules resonate. They vibrate like crazy, and that's what heats your food. But it can also be dangerous. The famous wobbling Millennium Bridge in London? That happened because the rhythm of thousands of people walking just happened to match the bridge's own natural resonant frequency. A total accident with huge consequences.
Okay, so let's pull all of this together. Why does any of this matter? Why should you care about this hidden rhythm? Because once you understand it, it really does change how you see the world around you. Think about the journey we just took. We started out with a nice, perfect, simple swing. Then we brought in the real world with the idea of damping. And from there, we saw how just applying a little push with perfect timing can unlock the absolutely immense and world-changing power of resonance.
So here's the big takeaway. Understanding oscillation isn't just some boring concept from a physics textbook. No way. It is the core principle that makes so much of our modern world tick. We're talking radio, medical imaging, musical instruments, even how we heat our food. It's this fundamental rhythm of the universe that we humans have learned not just to hear, but to control, and it has shaped everything around us. So from the buzz of the phone in your pocket to the way trees sway in the wind, this rhythm is, without a doubt, everywhere. The only question left is, now that you're in on the secret, where are you going to spot it next?